So we'll start with matrix inverses. Right? Before we continue, we'll quickly recap. So if you have a square matrix and it's full rank, then we can solve Ax equals b and x is A inverse b, and A inverse is unique, right? What is the interpretation of this operation? Yes, this is a change of basis, and that's essentially what the applications are about. Essentially, a change of basis for looking at data from a different perspective, right? And what basis are we changing to here? Whose basis are we changing? We're changing, so B is represented in the standard basis. We're changing it to what basis now? And what is the A basis? What vectors does it have, the basis? What are the vectors of that basis? It has n vectors, right? N vectors that form a linearly independent set. What are those vectors? Yeah? But what are those from the A matrix? Are they the columns or the rows? Yeah, the columns of A. So A1, A2, A. Okay. See, the place where this is applicable is when we're talking about time domain signals. Right? We know what a signal is, and imagine we have a signal like the one that is shown in this figure. Right? This is supposed to be the gauge pressure or respiratory pressure during normal breathing, and it kind of makes sense, right? So breathing is rhythmic, so you see the pressure goes up and down, right? And often, whenever we have a time domain signal like this, what we are interested in is, of course, we'd like to see the signal to roughly get an idea about what the pattern is. But we are also interested in being able to use this data and automatically identify different patterns in the data. And that pattern, or if there is a specific pattern that we find, then that might tell us something about the process that generated this data. Right? For example, maybe by looking at the pattern of the rhythmicity, you can say whether or not the breathing is normal, abnormal, and all that, right? So when we have data like this, we are essentially interested in finding out specific patterns, right? Now, we've recorded the pressure at each point in time at some sampling rate. So maybe, which gives us a set of numbers like this. If x of n represents this signal, okay, where n is time index, right? X of 0, let's say the recording started at time arbitrary time n equals 0. X of 0 gives the value of the pressure at the time. X of 1 gives the value of the pressure of the signal at time instant 1, so on and so forth. And often, see, for example, when you're learning signal processing, the early courses in signal processing will often talk about continuous time signals, and usually we'll talk about signals that are of infinite extent in time, right? But in practice, what we have is always a finite duration signal, often discrete or discretized signal, right? So often what we will have is a finite dimensional signal like this, where you have, let's say, n points that represent some information about the signal of interest. And what we often have is a time record like this, the value of the signal at different points in time. Right? Now, it's possible just by plotting the data like this, we can immediately see the pattern that we are interested in. That is, if you want to do it manually. Sometimes even if you plot the signal like this, maybe the pattern is not clear. Okay? Other times, if you want to automate the process of identifying this pattern, then of course plotting it is not useful for a human to view. You want a computer to be able to take this bunch of numbers and then tell you whether or not the pattern or a specific pattern that you're looking for exists or not. Right? So often there is a case for being able to either view process this signal on a computer and being able to view the signal from different perspectives. Right? As I said before, now because this is a finite number of recordings, we can think of each signal of length capital N as a n vector like this, right? As a n column vector. Because it's just a bunch of numbers, I can say I'm going to think of this as a column vector like this, and this is a vector from R capital N. Now, we know whenever we talk about vectors, and the moment you assign numbers to represent that vector, then you are essentially representing the vector of interest in some basis. Okay? And here we've represented this respiratory signal as a bunch of numbers, where the first value corresponds to the value of the signal at time 0, time 1, time 2, so on and so forth, till time capital N minus 1. Right? So this is the time domain representation of the signal. Okay. And we say it's a time domain representation because each index here, 0, 1 to n minus 1, represents the position of any particular position in this vector, tells you the time at which, or the time corresponds to the time at which the signal was recorded. Okay? The value here tells you the value of the signal at that particular time point. One way to write this is to say, okay, is to consider the standard basis in the time domain. Right? E1, E2 to E capital N. Well, any standard basis EI, what will it look like? It will be all zeros except for a 1 at the ith position, and then it's 0 again. So let's assume we were recording from some system, and then we found that the recording was EI. What would we say about that signal? Well, we'd say, well, the signal was essentially 0 except for this one time point at I. Right? That means this arbitrary signal that I've recorded here can be expressed as a linear combination of these EIs. Right? For example, I can write x of n, or I'm going to call this the x vector, as x of 0 times E1 plus x of 1 times E2, and so on and so forth, x of n minus 1 into En. Okay. You will find that this is in fact equal to this signal. Right? So this time domain signal we've recorded can be thought of as the representation of this respiratory signal in the standard basis, where the standard basis is E1, E2, En, right? And each of these is simply a, or EI is a time shifted impulse, right? Because it's 1 at a particular location, 0 everywhere else. Okay. So here E1 would simply be delta of n, E2 would be delta of n minus 1, and so on and so forth. Okay. In fact, another way to write your time domain signal is to write it as, write x of n as x of 0 delta of n plus x of 1 delta of n minus 1, and so on and so forth. Thus x of capital N minus 1 delta of n minus n plus 1. Right. This is how you would write it in DSP. If you were to take a linear algebra view, then you would write it like this. They are the same. We're simply saying this is, we think, because these are finite duration impulses, we are simply thinking of them as vectors in some Rn space. Okay, right. So this time domain signal is the representation of this respiratory signal in the standard basis, where the standard bases are simply time shifted impulses. Right? So now you could ask, well, if you view the signal as a vector, and this is the representation in the standard basis, you could ask, are there other bases in which maybe the signal looks a little bit more informative, or gives us more information than what can be obtained from here, right? For example, if I were to ask you, okay, there is some rhythmicity in this respiration process. For this subject, can we roughly say what is the time period of each breathing cycle, or the rate at which the respiratory signal is varying, right? Or for example, frequency. Well, one thing you could do is you could roughly say, okay, I'm going to find all the troughs, right? And then I'm going to find the distance between each consecutive trough, and then I'm going to take the average, and that's my average respiratory rate. There you'd have to do some processing to see this information. The question would be, is there another, because we are saying this can be thought of as a vector in Rn, and this is the representation of the vector in the standard basis, is there another basis where that information is more clearly or easily available to us? Okay. So it turns out there are, and that's essentially the topic, that's essentially, if we take this view that signals can be thought, finite duration signals can be thought of as finite dimensional vectors, then it turns out a simple change of basis is often very useful and reveals a lot of useful information. Then the question would be, what basis, right? The time domain signal is the standard basis. If we are talking about, there are of course infinitely many bases for any vector space, right? There are some bases that are very useful. The first one we will look at is what is called the discrete Fourier transform, which corresponds to the representation of any finite duration signal using what is called the Fourier basis. Okay. See, so far most of what we've dealt with have been real numbers, except for eigenvalues and eigenvectors, where we had to deal with complex numbers. Right? So it turns out here also we will now have to deal with complex numbers. So we will quickly review some properties of vectors from Cn, not Rn. Okay. So far we've seen vectors from Rn. We will now generalize and say we are interested in vectors in Cn. Okay. There are a few things that you'll have to keep in mind. So this means if I say x belongs to Cn, that means each xi is a complex number, okay, of the form ai plus j. I won't use I, I'm going to use j. I think I might have used j. Okay. If you see a j, that's essentially I. That's a habit from electrical engineering, where in electrical engineering you prefer to use j instead of I, because I stands for current. So this would be ai plus j bi. Okay, j is your square root of minus 1. Okay, we are using j instead of I. Okay. If x was from Rn, we defined a transpose operation, right? For example, if x belongs to Rn, it's a column vector. X transpose is a row vector. Okay. You can do the same thing for complex vectors as well, but a more useful operation turns out to be a generalization of the transpose operation, which is written as x raised to the power h. H stands for Hermitian. That's a Hermitian operation. What you do here is, let's say I have a complex vector 1 plus j and 2 minus j. X Hermitian is simply, you take the transpose of the vector and you find the complex conjugate of each individual element. Okay, so this will be first element here, second element here, and then you take the complex conjugate of this and complex conjugate of this. What is the complex conjugate of this? This will be 1 minus j, and this will be 2 plus j. Okay. Notice that if you only had real numbers here, right? Instead of, so let's say the imaginary parts were 0, the transpose operation and the Hermitian operation are the same, because the complex conjugate of a real number is itself. Okay. So the Hermitian operation is in fact a generalization of the transpose operation. Okay. In the case of real vectors, we could find the Euclidean norm of a vector, right, using the transpose operation. Right. What is this equal to? The square of the second norm. Right? This is like this. But if x, this is when x is real. If x was complex, right? So it turns out this is not correct. What is correct is this. Okay, that's this. And the standard inner product in the complex in Cn is not x transpose y, but it's okay. Now the transpose always comes with the complex conjugation. Right? If it's only real vectors, then complex conjugation essentially does not do anything. So the Hermitian is the true transpose operation that we are interested in. Okay? And you can verify that if you don't take the Hermitian, remember a norm, what are the properties of the norm, of a norm? What is definiteness? 0, right? If you don't take the Hermitian, right, and if let's say x is complex, we'll find that this in fact can come out to be a complex number. Right? So Hermitian is necessary. So if you use a Hermitian, then you're guaranteed this is greater than or equal to 0. Okay. Sorry? Oh yes. That's that. And then, for example, if you have a bunch of vectors x1, x2 to xk that are all from Cn, if you're taking the linear combinations, right, then a1 x1 plus a2 x2 ak xk, all the ai's now will be complex numbers. Okay, so linear combinations now will involve complex numbers as their scaling factors and not just real numbers. Okay. And then the last one, again, if you have A now, which is a complex matrix, n cross m, what would this be? For example, let's say I write 1 minus j, j, 4, 2 minus j. Say this is A. What would be A Hermitian? Yeah, this is a 3 cross 2. So A Hermitian would be 2 cross 3. What would be the first element? J. And yeah. And notice that because this is defined as the standard inner product, when are two vectors in Cn orthogonal to each other? What is the condition in Rn? X transpose y is 0. So here, when x Hermitian y is 0, then you say the vector x from Cn is orthogonal to the vector y from Cn. Sometimes you might see people write a star. That is also often used to represent the Hermitian operation, H or star or the asterisk. And then the last thing I want to say, or maybe I'll write here, orthogonal matrices. Symmetric matrices would be okay. In Rn cross n, we talked about orthogonal matrices, right? What were those? Do you remember what is an orthogonal matrix? It's if A is Rn cross n, when do we say it's an orthogonal matrix? Yeah? Yes. Another property? What about its inverse? Does the inverse exist? Why does the inverse exist? It's square, so we can ask whether the inverse exists. Why does the inverse exist? It's full rank because the columns are all orthogonal or orthonormal. That means they're linearly independent. Okay. So what? So what is the inverse for the case of an orthogonal matrix? Yes, A inverse is A transpose. You have a similar situation in when you have n cross n. Okay. The columns form an orthonormal basis. Okay. That means for each column, AI Hermitian AI is 1. AI Hermitian AJ is 0 when I is not equal to j. Okay, that's what it means to say the columns form an orthonormal basis for Cn. And the condition here would, what is the condition in terms of its inverse? The inverse exists because the columns form an orthonormal basis. What would be the condition for the inverse? Yeah, A inverse is what? That's all. Hermitian. Okay, and I don't know why these have a different name in Cn. These are called unitary matrices, not orthogonal. If you hear the term unitary matrices, then you're talking about matrices from C n cross n, and the columns form an orthonormal basis, so the inverse is simply the Hermitian. Okay, all right. Just those basic identities. We'll now move on to look at what is the Fourier basis. Shall I wipe this off? Okay, let's say we have a sinusoidal signal like this, right? Sine omega t plus phi and some amplitude. Okay, let's say we fix the frequency, but the amplitude and phase are free to change. Okay, that's the problem we have. Omega is fixed. We agree on omega, but a and phi can be arbitrary for the signal. Okay, that means to specify this signal completely, I need to give you two pieces of information. I need to give you A and I need to give you phi. Okay, that's one way to convey the signal to you, right? We've agreed on omega, and I tell you A is 1 and phi is 0.5 pi. Then you know what the signal looks like. So that's, I can either give you the magnitude and the phase, or it turns out there is another way to represent this. What will happen if you expand this? What is sine A plus B? So it will be sine A phi plus A cos omega t. Okay, we've agreed on omega. So if I tell you this information and this information, if I tell you A cos phi and A sin phi, you can figure out both A and phi from that, right? So that's another way to represent the same signal. So A cos phi into sin omega t plus A sin phi cos omega. Okay. If we know that an arbitrary signal that we are interested in is essentially a sum of, let's say, a bunch of frequencies I from 1 to, let's say, capital N. Okay, that means the signal is always of this form: A1 sin omega 1 t plus phi 1, A2 sin omega 2 t plus phi 2, and so on and so forth. An sin omega n t plus phi n. Okay. So if I were to completely describe the signal to you, all I would have to give you are these AIs, AI to AN, and phi I to phi n, or I need to, or essentially I have to give you what? 2n numbers. Okay, these could be AI phi I, or these could be AI cos phi I, AI sin phi I. Okay, I could give you either of these two. We often choose this. Okay, even though this is easier to interpret, We often choose this because it turns out it's more convenient to work with these numbers mathematically than to do this. Okay? And what I mean by that is this. If, let's take this example, right? This is our simple x of t. If I were to take this, right, then it turns out I can represent this signal x of t as a sum of two signals like this. For example, if I have sine x, right, I can write sine as e power jx minus e power minus jx divided by 2j. Or I can write cos x as e power jx plus e power minus jx by 2. Right? It turns out instead of working with sine and cos like this and writing a summation formula for a signal like this, it's a lot easier to represent sine and cos in terms of e power jx, and it's easy to represent x of t as some complex number a multiplied by e power jx plus another, I'm going to call it a1, a2. Okay. So this linear combination that you have of sine and cos can more conveniently be represented as simply a product of a complex e power jx and this is a complex number. So instead of representing our sinusoids as sin omega t or cos omega t, we choose to represent our sinusoids as e power jx, where e power jx is simply cos x plus j sin x. Okay. And from now on, we'll essentially use this to represent sinusoidal signals. Okay. And the Fourier basis is essentially a basis of sinusoids. And the reason sinusoids are used is because we are interested in rhythmic behavior, okay, something that changes periodically. And sinusoids are well, simple periodic signals that naturally occur. So we essentially work with them. And they also have some nice properties because they are eigensignals of linear systems and all that. Okay. So the Fourier basis is essentially now a basis consisting of a bunch of sinusoids of this form. Okay. So when we started with, we were talking about signals from Rn. Okay. We will now generalize this and say if it's a function of if it's an element of Rn, it's also an element of Cn. Okay. So we'll simply treat this as signal that is sitting in Cn, because these are all complex numbers with no imaginary part. Okay. If that is the case, we'll now define another basis, okay? Or we'll our time domain signal, right, was represented in this base E1, En. For the Fourier basis, we define another set of signals. If you want to define a basis, you need to have n signals, and those signals have to be linearly independent, right? And the individual elements of so this is the standard basis. The Fourier basis is a bunch of signals W1, Wn, okay, and each Wk is defined according to that expression. So Wk is essentially a time domain signal Wk of n, okay, and Wk of n is defined to be e power j 2 pi k by capital N. Okay. Don't worry about why does it have this weird 2 power k by n and all that. For now, just take it as this is the definition. Okay. That means this is essentially cos 2 pi k by n plus j sin 2 pi k by n, and k is now a number that varies from 1 to 0 to n minus 1. Now, if you were to put each of these time domain values in a column vector, that is your Wk. Okay. So, what we are essentially saying is Wk is a sinusoid or a complex sinusoid with frequency 2 pi k divided by n with digital frequency. Okay. When k is 0, that's essentially DC. Okay. When for higher values of k, then you have a time varying signal. As the value of k increases, you have sinusoids that vary faster and faster. Okay. If we define a bunch of signals like this, right, it turns out they have a very nice property that any two Wk's, right, are in fact orthogonal to each other. So yeah, you notice I've used star and H. I should be using H there, but that is true. If you take any two vectors, Wi and Wk, right, and you take their standard inner product, okay, this will be 0 when I is not k, but when I is k, what you get is n. Okay. Okay. That means the Wi and Wk are orthogonal to each other when I is not k, but when it is k, the square of their Euclidean, of the signals of the vectors Euclidean norm is capital N. That means it's not of length 1. Each Wi is not of length 1, but it's orthogonal to every other Wi. Okay. So if you do want to orthogonalize it or orthonormalize it, what do we do? So we know that the vectors are orthogonal to each other, but they are not of length 1. Each of them is of length root n, okay, because the square of the Euclidean norm is n. Now, if you simply take each one of them and divide it by root n, then you're fine. Then this will be 1 because this has a divided by root n, this has a divided by root n. So this whole thing is divided by n, and the inner product is n, so n and n get cancelled. Okay. So if we now define a basis or a set like this, this turns out to be an orthonormal basis of complex sinusoids. Okay, and this is essentially your Fourier basis. Fourier basis for the discrete Fourier transform. Okay, because discrete Fourier transforms deal with finite duration discrete time signals. Okay. If that is the case, how would I have my original signal x in the time domain basis, which is the standard basis. Now I've defined a new basis called the Fourier basis like this. Okay. How do I change basis from the time domain from the standard basis to the Fourier basis? How would I do that? Yep. You understand the question? I have the standard basis, I have my Fourier basis. I know the representation of my signal in the standard basis, which is x. How do I find the corresponding representation of my time domain signal in the Fourier basis? How did we change basis earlier? Here, you had B in the standard basis. To change it to the basis of the columns of A, what did you have to do? Well, you had to first form a matrix like this with the columns of A, and then take its inverse, and then multiply it by B. Right? That's what I've written here. Right? So you essentially do the same thing here. We now define a Fourier matrix called Fn. Okay. Note that there is a 1 by root n in each vector. So we take the 1 by root n out, and then you simply make W0 to Wn minus 1. Well, I've written it as W1 to Wn, but this will follow this notation. Okay. You stack them as then stack the individual columns, form a block row, and that's an n cross n matrix. Okay. The columns of Fn are an orthonormal basis for Cn. Okay. then what can we say about Fn inverse? Okay, and notice Fn is it's from Cn cross n. The columns form an orthonormal basis for Cn. That means this is simply equal to orthogonal matrix, unitary matrix, right? So you can verify that in fact Fn Hermitian, Fn is your identity matrix. Okay. Okay. So now so we know the representation of x in the time domain. How do I get the Fourier representation of the same signal? This is the time domain representation. We want to change it to this basis. Yeah. Yeah, tell me. Take Fn. You have to do the inverse, but inverse is Hermitian, so Hermitian you simply do that. And this is now the representation of x in the Fourier basis, and this is essentially your discrete Fourier transform. Okay. Yeah, xf is simply Fn Hermitian x, and that's your discrete Fourier transform. And now if you have the Fourier representation and you want to get the time domain representation, what would you have to do? Yeah? Yeah, you simply do Fn, right? And what is this? Sorry? Yeah, this is your inverse discrete Fourier transform. Okay. So by appropriately choosing your Fn or the basis, right? In this case, the Fourier basis, we are converting between a time domain representation of a signal and its corresponding Fourier representation and Fourier representation to the time domain representation. Now, in the time domain representation, right, what does xi tell me? The value xi tell me? What is the interpretation of that number in the time domain representation? I tell you xi is 4 millivolts. What does it tell me? Yes, exactly. At time I, the signal had a value of 4 millivolts. Okay. How do we interpret this? I'm going to call it xfi. The ith component of the representation of the same vector in the Fourier basis. Okay. The interpretation of this, right, is simply this tells you how, I'm going to say just how much for now, how much of e power j 2 pi, I call it I divided by n to n. This complex sinusoid is in your original time domain signal. Okay. If let's say x of I was 0, right, then your original time domain signal has no frequency component at this frequency, 2 pi I by capital N. So this x of I simply tells you how much of the ith frequency is in your original signal. Okay. Whereas in the time domain signal, xi corresponded to the value of the signal at time I. In the Fourier representation, this is how much of my ith frequency is there in my original signal. Okay. 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 Let's maybe do a numerical example. Okay. This file is shared, so you can go and look at it by yourself. You can look at the individual functions that it defines. Fourier basis is a function that's defined later in the notebook. So you can go and modify this and run it and then see for yourself. Let's say we define a time domain signal, a sinusoidal signal with amplitude 1, amp, freq and phase are the amplitude, frequency and phase of the sinusoidal signal. Amplitude is 1, frequency is 1 and phase is set to 0. I generate the time domain signal, okay, and then this is x, okay, that capital Fn is my Fn matrix, okay. If I want to find the Fourier representation of my x1 signal, then all I have to do is I take Fn Hermitian. In NumPy there is no Hermitian operation, so I take the complex conjugate and then the transpose, and at here simply means matrix multiplication, because star stands for scalar multiplication. The alias sign is for matrix multiplication. So I do Fn Hermitian x1, then that gives me my Fourier representation. Okay. Now, if you look at x1, no, the way I've defined it, it's of amplitude 1, phase 0 and frequency 1. Okay. And if you look at the way I've defined it, my x of n, or x1 in this case, is defined as 1 times cos 2 pi, frequency is 1, so this is 1 divided by n is, I don't know what capital N is here, capital N is 5. This is x1, okay, and this defines my vector x, which is a 5 vector. This is in fact now a vector from C5 because capital N is 5. That's my time domain representation, and that's essentially this signal 1, 0.309 minus 0.8 minus 0.8.309. So if you were to compute the value of the signal for time starting from 0 to 4, those are the numbers you'd get, which I call the standard basis representation. Okay. Now, if I take this x, right, and then I do F5 mission, I get xf. I put 5 because here capital N is 5. Okay. Then what I get is now a bunch of complex numbers like this. Okay. If you look at this, right, all of these are 0 except for this one signal. Okay. That's essentially because there is only one sinusoidal component here, okay, which was a frequency 1. Let me run this again. Okay. This is your x, this is your xf. Okay. The first number is 0 plus 0, second number, third number, fourth number, fifth number. 5 numbers again. Right? But if you look at this, right, all the numbers are 0 except for these two numbers. Right? That's because if you look at this signal, right, this looks very much like my one of the basis signals, right, which was of the form e power j 2 pi k by n. Okay, if you look at this term, right, this looks very much like that. Okay. So it turns out when you compute the Fourier of this, you have a lot of 0 values and a few non-zero values. Okay. And see, notice that these are all a cos theta plus j a sin theta. I can compute the magnitude and phase of each of these complex numbers. If I compute the magnitude, right, the magnitude is non-zero only for 2 numbers and the phase is 0 for all of them. Okay. Now, if I go and change my original signal, let's say the phase was initially 0. Now, let's say I say the phase is 0.25. Okay. That means now this is not 0 anymore, but this is pi by 4. Okay. Hold on, no. In fact, I'll set the phase to, let's say, it's 45 degrees. Okay. They run this again. The magnitude has not changed. Okay. What has changed is now it says, well, at this location the magnitude is 1.12, but the phase is 45. Okay. That's because I set the phase to 45 and saying I see one component with the non-zero, one sinusoidal component with the non-zero amplitude and phase, and the amplitude is 1.12 and the phase is 45 degrees. Okay. If I were to go and change this again, let's say I set it as minus 90. Okay. So what I'm essentially trying to show here is if you have a signal that is a sinusoid, right? And if you look at this representation, right? The vector has almost all the values are non-zero, okay? Except maybe for the first one. But when you transform the signal from the standard basis to the Fourier basis, in this particular case, most numbers are zero except for a couple of numbers here. Right? If you look at this, most are zero except for these two. Okay, that's because the signal that we originally started with has a rhythmic pattern that fits well with the pattern of signals that you have in the Fourier basis. That is why it has a lot of zeros. Now instead, if I go here and change the frequency to 2, you see that 1.12 has shifted now to another location. Earlier it was here and here, now it's moved here because now I've changed the frequency to 2. Okay. If I change my frequency to 0, that means this is essentially a DC signal. I should only see one non-zero value, which will be the first value. The magnitude of the first number should be non-zero, everything else should be 0. In fact, why? That's because my phase is 90. There. Here it says there is only one frequency component, every other frequency component has 0 magnitude, right? And that frequency component is essentially DC, constant value. Okay. You can play around with this, we'll come back to this a little later. Okay, all right. So the point I'm making is this, right? Let's say your original time domain signal looked like that, x1 of n, okay, which is a times sine with some frequency 2 pi 50 by n. Okay. For now, we'll assume that capital N is larger than 50. Okay. And that signal looks like this. Okay. If you had to represent this as a vector, then you take the individual values of the signal and then put them in a long vector. That will be your time domain representation x. Okay. So the time domain vector for this x1 of n is a long vector with a bunch of non-zero values. Okay. Now, if you simply now ask what does this look like in the Fourier basis, right? You do a change of basis to the Fourier basis. What you get is this. Okay. In the Fourier basis, I'm only showing the magnitude. Okay. The magnitude is all 0 except for this one location. Okay. So essentially it looks like this, it's a bunch of zeros and then a non-zero value, I put it star, and then it's all zeros. Okay. So you would say, at least in this case, this signal looks a lot more cleaner in the Fourier representation, which we're calling the frequency domain representation, when you use the Fourier transform. That's primarily because the signal that you started with, the x of n that you started with, looked like one of your basis vectors, because your basis vectors are essentially of that form. Okay. So whenever you have a vector b that looks like one of your basis vectors, then you get a nice clean representation like this. In fact, what is this vector? Where everything is 0 except for one vector. This has the look of as a unit vector. Right? Now you could ask, okay, what if x1 of n was not just a sine some frequency of n, but was a sum of a few sinusoidal components like that? Right? Now let's say you have a more complex signal, which is a bunch of sum of sinusoids of different frequencies, and it looks like this. This is clearly not a simple looking signal, this is looking complicated. Okay. But if you take the Fourier representation, what you find is a very nice view of the same signal. It's the same signal, it's not a different signal, right? But in the Fourier domain, everything is 0 except for these 4 locations, and those 4 locations correspond to different frequencies. Right? So even though here it's not clear what frequencies are present, if you looked at this, I'd probably say, well, maybe there is one, maybe there are 2 or 3 frequencies. But if you do the Fourier, you find there are exactly 4 frequencies of these different amplitudes. Right? So what the Fourier basis allows you to do, especially if you're dealing with rhythmic signals, right? It gives you or it emphasizes the frequencies of the rhythmic components that you have and kind of makes them stand out, right? Essentially telling you what frequencies are primarily present in your original signal, okay? Which is not immediately clear if you directly look at the time domain signal. If I showed you this and asked you, tell me what frequencies are present, maybe you might or might not be able to say. You might have to do some calculations to tell. But if you transform it to the frequency domain representation, then it's immediate. You can immediately read off what the frequencies are. Okay. I'm going to stop with this last one. Okay. Okay. Let's say now we take a different single sinusoid. Okay. That looks like this. You take the Fourier representation. You remember earlier when it was 2 pi 50 by n. You remember what the frequency domain representation looked like? It was all 0 except for this one. Except for one position, everything else was 0. But if the frequency is now some 2 pi 76.1 by n, it still looks like there is a sharp frequency component or very tall frequency component, but it's not that clean anymore. It looks like this. That means there is a large non-zero component, but there are other smaller non-zero components as well. Okay. That's because even though this is a pure sinusoid, if you look at the frequency, right, it's 2 pi 76.1 by n. But if you look at the Fourier basis, right, Wk is of the form e power j 2 pi k divided by capital N into small n, and k is a number between n minus 1 and 0, and k is an integer. Whereas here, that frequency, this is supposed to be your k, this is not an integer. Okay, so this signal, so the reason you get more non-zero elements than in the case where it was 2 pi 50 by n was because, or is because, this x2 of n, right, this signal actually matches with none of these perfectly. Okay, because the frequency does not match with any one of them, right, because here k is not an integer. Okay, when you have a situation like that, I mean, I would say this is still better than this, because here I can at least say the frequency is somewhere around here, right? That's the biggest component. Whereas here I'll have to do some calculations to find out. The moment I transform it to the Fourier domain, it's at least a little bit, at least it's immediately apparent what the or the major frequency component is, right? So the point I'm trying to make now is, if you have the DFT, if your original signal had frequencies of this form, 2 pi k by n, where k is an integer, then you will find that there are these sharp, clean peaks that occur in your DFT. If it is not of this form, if k is some real number, then you would still see peaks, except that it won't be that clean. You'll now need, you'll have other non-zero values around that peak as well. Okay, that's because you are now trying to represent this signal, which does not match with any of your original basis signals, with your basis signals. Whereas earlier, when this was just 2 pi 50 by n, this signal exactly matched with one of your basis vectors. So you only have to use that basis vector to represent the time domain signal. Because this does not match exactly with any one of them, you have to now use all of them to kind of then perfectly represent this signal. Okay, all right. So we'll stop here with that. I would say, please, this is available on the GitHub page. I would request you to go and review this material today, so that tomorrow's lecture becomes a little easier. And if there are any questions about what we've covered so far, please let me know tomorrow. Thank you.